So I'm going to do the first problem on the board. And one thing that the first problem I'm referring to this the ring one, and they have to find the charge distribution and all that stuff. So I'm going to do that one. What we need to remember, okay, not that. Can you guys see red on black? Is that? Oh my God. Let's see. Let me change my pen color. No, I think it's because the red doesn't appear very well on the screen. I think the projector is just that crap. You see it? Okay, but it's still not like perfect, right? Is that better? Oh yeah, that's way better. Okay, so you have a ring. Okay, that doesn't work either. You have a ring, right? And this is not a disc, it's literally a ring, and it's infinitely thin, and therefore on the inside of it there's nothing, and there's no thickness either. And what you guys needed to do to figure this one out is to understand that if you were to cut that just at any point along that circle, then this breaks up to be just a line. Okay, and it's what this the trick is to this problem, I suppose. And you always start with, if you know it's a line, you use lambda, sigma, or rho. You use lambda, and if it's lambda, it's times the length, and the length is this length here. Now, the difficulty part about this is that you set up the integral and you're like, all right, fine, I solved most of the problem by now. So lambda, that's 1.5 sine square theta dx. Oh my God. Oh, it's because I'm on the edge of the. So 1.5 sine theta dx, right? But you can't integrate something that uses two different variables, right? It's illegal in calculus. So you have a dx here, and you have a theta here, and you can't integrate that, all right? Wrong. All right, perfect. So now you have to figure out, okay, so if I'm finding the little charge dq of this line here, dq, and its length is dx, right? That's what I've been doing so far. Then I got to find dx in other terms. So if I were to draw that dx here, right? So let's call this dx, right? One small arc length of my circle. That small arc length of my circle, if this was radius r, is going to be expressed as, well, dx is equal to the radius times d theta, which is this angle here. Okay, so now I can rewrite this as 1.5 sine squared theta times r d theta times r d theta. This is equal to 1.5 r integral of sine squared theta d theta. Now, if I want to put the limits of my integral here, if I'm using theta now, which angles do I need to integrate over? 0 to 2 pi, exactly. Right? And that would be the answer that I was looking for. Okay. One thing that I noticed is that some of you are just randomly adding the dx or the d theta as if it were inconsequential to the formula. You can't do that, right? Because d theta or dx still carries an angle with it. All right. So, like, for some of you were saying, okay, well, if the arc length is r delta theta, so you're saying that, no, right here, you're saying that the integral 1.5 integral sine squared theta, and then you're like, okay, and you have to multiply that by the arc length, right? So then you do r times delta theta, because I've given you that part in the question, and you know you have to use it. and then you add a d theta here to make it an integral. What you can't inconsequentially add a d theta and expect the formula to work out, because this carries with it units and a dimension and everything. So really, this had to replace this. This was too much. Okay. So think about what those dx's, d thetas, dA's, dv's, d whatevers are, and try to make sense of that when y is in that equation. Okay? Any some questions about this? Give you guys a second to write it down. Do you want the lights on or off? Off? No, I'll give you the contrast. This is on. No? All right, fine. It's just way too dark now. I feel like we're in a cave. All right. So I'm going to move on. The second problem on the quiz wasn't so poorly done. It was actually much better, and I'm happy about it. There's just a lot of you aren't thinking of which kinematics formulas to use. Essentially, you guys, most of you got the acceleration, and the acceleration was q delta v over r times m. That gives you acceleration. And then you had to do vf squared equals vi squared plus 2a delta v to solve for vf, to solve for vi squared. Because remember, when a projectile motion reaches its maximum height, its velocity at the height is 0. Okay, so that was you just made it 0, and then you had q, you had a, you had delta v, which was the separation of the two plates. So you can find what vi was. And then when you solve this, this wasn't actually vi, this was viy. So you have to do sine 5 is equal to viy over vi and solve for vi. Okay? Yeah, Isabel. In this case, I can't remember which version of the problem you guys had, because some classes was positive, some was negative. In this case, the acceleration is negative because it's pointing downward. Yeah. Okay. Okay, so what you have to remember is when you solve for that acceleration, it's going to give you a scalar quantity, right? So that's just the magnitude of the acceleration. But looking at the electric field and what kind of object you have. So you have a proton, right? That's going to enter a field where the field is pointing downwards. So a proton entering a field going downwards means it's going to accelerate downwards. So you have to know that it was negative. Okay, so far so good. Let's move on. There's two parts in today's class. First, I'm going to review what we did last class, and I'll remind you right now that what we talked about last class, before the lab, was electric fields and electric potential, and also potential energy. Now, we're going to review that today. I'm going to ask you guys to do some problems. All right, I want you guys to work in pairs or in triples and quadruples or however you wish, but just not alone. All right, please don't work on this alone. And once we're done that, I'm going to introduce a new subject called Gauss's law. This is, I'm sorry to say, the hardest part of the course is today, and well, starting today, and then next class we're going to get into it really hardcore. It's not easy, it's very abstract, and it can cause quite a bit of confusion, and this is also the last subject, like last big subject before the test, okay? So this will be included on the test that's going to come in as the next week. 2 weeks. Okay. Did I scare you there? Yeah, so let's get started. So you guys all remember this. Are these equipotential lines or electric field lines? Do you guys know? Are these equipotential lines or electric field lines? Equipotential. All right. I'd like to talk to non-zombie people. So those of you who are alive, say something. And those of you who are saying something, say it with open enthusiasm. Equipotential. All right, yeah, so they're equipotential lines. And if I were to draw electric field lines on this, how would they look like? What strategy do I use or what technique? Wake up, guys. Don't make me turn on the lights. Zach. Yeah, perpendicular to the equipotential lines. Are they, so is electric field a vector? Yes. Does it need arrows? Yes. Okay, so if they're perpendicular to the equipotential lines, are they going to, if I were to draw this one, so here's one that's perpendicular, oh God, that, look, that's perpendicular to all of those lines. Is it going towards the left or towards the right? Towards the right? How'd you get that? It's going outwards, but how do I know? Like, it always goes, remember, electric field lines, it goes towards the negative or away from the positive. Sorry? Exactly. And so based on what information you have there, where's the negative? Is the negative in the middle or is the positive in the middle? Look at those voltages. Are they increasing or decreasing? They are decreasing? They're decreasing. They're negative, right? So they're decreasing. So there you have minus 16.1. Here is negative 9. So it's actually, if you're going towards the left, the numbers are decreasing. So the arrows go in that direction because that's where the negative is. All right. So if I were to draw all of my lines, it would kind of look like this. Well, I can't go through that charge, but sure. It would look something like this. I mean, it's not perfect because I'm not MATLAB. It will look something like that. Okay? You okay with that? So there's that. So today we're going to review this concept of potential and potential energy. So we're doing the same class objectives as last time. So just remember that an electric field depends on space, and it's the force on any charge. So the newtons per coulomb, if you guys remember the units, and the electric potential is the same thing, but at this time it's energy per charge. Okay, and it's a scalar quantity. So this is a vector, and this is a scalar. Oh, never enough room here. Scalar. Okay, and that's pretty important. Today we're going to use those concepts really heavily, right? So remember the fact that potential, electric potential, the thing that's measured in volts, is a scalar quantity, and electric field, the thing that's measured in newtons per coulomb, is measured as a vector quantity. Okay? Very important today. Electric potential or voltage is defined as the work done per charge. This relationship here in the middle is pretty important. All right. However, this bottom one for today is going to be important, but I want you guys to make a change to it. It says delta V is equal to KQ over R. That's not true. It's just V is equal to KQ over R. Okay. It's not delta V. It's V. All right. Remember our units, joules and volts. Joules and volts both are scalar quantities. And which brings us to our first example. All right, so we're going to do this one together. And then the next few I want you guys to do on your own. There's two questions here. Find the electric potential at the dark point. So at this point here. Oh no, now my yellow doesn't work. Oh, you guys can see it, right? Yeah, okay. So how much work must be done to bring a proton from infinity to that dark point? And we'll do that right after. So first thing that we want to do is calculate the voltage or the potential at that point. So what's the formula? Do you guys remember the formula for voltage? It was literally on the slide before. And I asked you to cross out the delta. What was it? Yeah, very good. KQ over R, so voltage is equal to KQ over R. And that's pretty, this one's going to be pretty straightforward. You'll see. If I wanted to calculate KQ over R of this point, based on this, and I just need to add the KQ over R based on this point. So I'm just going to change the color here. All right. So I have my point there, and I have, let's call this Q1, and let's call this Q2. And my total voltage would just be voltage from 1 plus voltage of 2, which is equal to KQ1 over R1 plus KQ2 over R2, which means that it's K, oh my, K plus 2Q over R plus, oh no, it's not 2Q, it's 2 nanocoulombs. And this is 0.05. Okay, that would be for the first one. Multiply or plus negative K times 1.0 nanocoulomb over 4 centimeters. Okay. Did I take into consideration how far and which direction those charges were? Like, did I treat this one any differently than this one because of this angle? I did not. That's where the non-vector comes into play, okay? If it were electric field, right, what you guys would have to do is be like, all right, well, I have to find the electric field in that direction and the electric field in that direction. Or no, actually, it would be in the opposite direction for this one. It would be in that direction, right? So electric field in that direction, electric field in this direction, and then try to find the resultant electric field in that direction, right? I'm not asking you guys to do that because I'm not asking for electric field, okay? It's simple. It's just scalar. We're just adding the two numbers together. Does someone have a number for me? I have a challenge for you guys. Try to do this calculation in your head. It's not hard, I promise. What is the value of K? 9 times 10 to the 9, and nanocoulomb is 10 times, or 1 times 10 to the which unit? To the which exponent? Minus 9. So something times 10 to the 9 times something times 10 to the negative 9, well, those two will cancel each other out. So essentially, you're going to have 9 times 2 over 0.05. When you divide by 0.05, that's the same thing as multiplying by what? By what? 20, exactly, right? So 9 times 2 times 20 is what? So 9 times 2 is 18, times 20 is 360. So that's 360 volts, right? So I can cross that out. Plus, well, 9 times 1 divided by 0, dividing something by 0.04 is the same thing as multiplying by what? If you divided $1 by 25 cents or 25, it would be, eh? Times 25, right? So dividing it by 0.04 is the same thing as multiplying by 25. So it would be 9 times 1 times 25. So what's 9 times 25? 225, and this is a negative number because it's a negative charge, right? So now we have 360 minus 225, and that should give us our final answer, which is 135. What's that? Okay, but that's because you used 8.99, right? Yeah. So 135 volts, that's the potential at that point. Now, if I were to ask you, how much energy does it require to bring a proton from infinite to this point? It's super easy. That question makes no sense whatsoever because it's worded so complicated. But what I'm only asking you is, what is the potential energy at that point? And if you want to find potential energy, it's voltage multiplied by charge. So QV is equal to potential energy. And what's the charge of a proton? Yeah, but I mean the delta V is V0. Yeah, exactly. When it says infinity, 0. All right. What's the charge of a proton? 19. Yeah, Coulomb. All right. So I just have to multiply my 135 volts by that charge, and that'll give me the potential energy of my proton at that point. Okay, I'm not going to do it, but that's all you need to do. That's all you need to do. All right. Yeah. Explain that. The QV equals PE. So you have to remember that potential is potential energy per charge, right? So voltage is equal to potential energy per charge. So I just rearrange it to get potential energy. Yeah. Okay, so here's the point. I want you guys to do the next series of examples in groups. All right. And once you have the answer for one, put up your hand. Let me know what you have. I want to see your reasoning, and then you can move on to the next one. Okay. So I'll give you guys. Let's try not to take more than 45 minutes to do these next few problems. All right. So let's go do that now. I expect to hear lots of talking. I want you guys to talk. I find my class way too boring. So do that, please. All right. Let's We're going to talk about some guy named Gauss. And Gauss, like him or not, he's going to be your best friend in this part. The reason for that is because he's going to make it so that you don't have to do so many really, really complicated math, a lot of complicated integrals. He'll make it so that you don't have to do that. He came up with something that we now call Gauss's law. He didn't call it Gauss's law, and I think he came up with something and he called it Gauss's law. I figured out Gauss's law. So yeah, so you can look for one. It looks complicated because it's going to have a lot of symbols that you've never seen before. And in order to understand it, there's a lot of math, but in order to apply it, is actually very simple. Okay? So we're going to do the complicated part, which is the understanding it and showing you the symbols and all that stuff. And you guys are going to do the easy part, which is applying the rest. Before I do that, I want you guys to get an appreciation for why we need Gauss's law. Okay, so here I have a ring. Oh, this is bad again. Change it. At the top left here, I'm going to draw a ring. All right. And what you guys did on your quiz is you found me the charge, which is, haha, super simple. even though you guys might not agree. But the ultimate point of all this is to find the electric field, all right? Because anything that's charged is an electric field, and knowing the electric field of an object is incredibly, incredibly important in the fields of, hydroelectricity and all those things, high-powered lines running through the city and drastically affecting things. So it's really important to be able to understand the electric field. Electric field is the thing that we want to get. Now, okay, how do we find the electric field at that point? Well, it's not easy. Okay, so the first thing that we need to do is we need to define that this dot, this point, is at a distance. We're going to call this distance r, h. Sorry, h. And this ring has a radius r. Okay. And if you wanted to do this hypotenuse here, we're going to call that capital R. And so at this point here that I just highlighted on the ring, that point is going to provide, and let's say this is a positively charged ring, right? That point is going to give an electric field at our point of interest in which direction? In which direction is the electric field going to be going because of this point? Yeah? Yeah, exactly. It's going to be going away from it. So at that exact point, right, there's going to be an electric field from one of those little tiny segments of the ring going in that direction. Now, if I were to just extrapolate this line and go straight up a little bit, I can tell you that this angle here, the angle that's being created, and this angle here, so if you're not, they're going to be, they're going to be what? The same, right? Because if you have any two lines that intersect, and if these two lines are straight, then these are angles opposés or opposing angles, depending on which language you learned it, and you end up getting the same angle. So this angle here is equal to the same angle here. Now, I'm going to erase this later on, so I don't know if you want to draw it or not, but opposite from this circle, from this dot on this circle, so right there, right, there is another point, right? There's another point that's going to give an electric field to there and in the opposite direction, right? Are you guys following? So those x values of those electric fields are going to cancel each other, right? And the net electric field is going to go in the up direction. Are you guys in agreement? The net electric field at that point is going to be in the upwards direction. And along this circle, because this is a symmetrical shape, along this circle, you're going to get symmetrical cancellation of all the x values of the electric field. So if I were to integrate all the electric field at this point from all the different charges around this circle, then you're going to get something that goes straight upward. Okay? Because all of those side angles will have canceled each other out, and all the y components will have added on to each other, and you'll get this huge electric field going upward. You guys following so far? It's about to get fun. So now let's go back to just that one charge. I'm going to delete. Oh, yeah. Okay. Draw my circle again. All right, I'm going back to my one charge. And so we know that down the line, the x component is going to get canceled out. So now I'm just going to assume that the electric field is just upward from that one point. And I don't care what the x value is. I care only about the y value. And it's still important that this angle, we remember that that's an angle theta, and that's equal to this angle theta here. That's okay? So if we want to find the electric field from that one point, dE, all right, so that's the electric field at that point from only one part of this ring. All right, well, I need to know that, it's K times, okay, dQ, because it's a small charge there. divided by capital R squared. But wait, there is more. That's for the diagonal component. That's if my electric field was going in this direction, right? But I told you that this part of it's going to get canceled out and only the y part's going to get left over. So I'm just going to add a cos theta here to account for that. Okay? Because remember, cos is adjacent over hypotenuse. So the adjacent component of this thing, if I take this angle and I find the adjacent component, it's the y dot. All right, so you can, if you want, you can call this DEY if it's confusing. And this is the ring. So there is a linear charge density multiplied by, and you guys know this from your quiz now, times the arc length, and the arc length is d theta. Okay, so now we can rewrite this as DEY is equal to k times lambda times the radius times d theta over r squared. All this multiplied by cos theta. So what I did from this first step to the second step is I replaced dq by the arc length multiplied by the charge density. Okay. I'm still not done. You guys said that this top angle and this bottom angle is the same, right? This angle and this angle is the same. And cos of that angle and cos of that angle are the same as well, right? All right, so the cos of angle is equal to adjacent over hypotenuse. Adjacent over hypotenuse, is that right? Yeah, adjacent over hypotenuse. So adjacent over hypotenuse, right? So I can replace that. So DEY is equal to k lambda times r d theta over r squared multiplied by adjacent, oops, not squared, over hypotenuse. And if the hypotenuse is a function of h and r, I can say that it's the square root of r squared plus h squared. Okay, that's the hypotenuse, right? Let's go further and get even more complicated. Yeah. The height. Yeah, it's starting to get hidden now. We'll have r squared at the bottom there. We can get rid of that r squared and express it as a function of h and r. So we can say that now DEY is equal to k lambda r d theta h over, and this r squared is h squared plus little r squared times, now I have this square root. Something to this, the square root of something is the equivalent of giving that which power? What? In to me, 1/2, exactly. So that's the same thing as writing h squared plus r squared to the power of 1/2, right? So remember, this is r squared. So if I took the hypotenuse, which is the square root of h squared plus r squared, and I squared it, then that's just h squared plus r squared, right? And then I rewrote this as a function of 1/2, which means I can also rewrite it as DEY is equal to k lambda r d theta h over h squared plus r squared. And when I multiply two things, what do I do with their exponents? You add them, right? So 1 plus 1/2 is 3/2. Are you guys liking math so far? Yeah. Okay, so think about it as a right angle rectangle. If I want to find out what the hypotenuse is, because that's the distance between this point and this point, right? The formula is kq over r squared. So that r is equal to the square root of h squared plus r squared. And I'm asking you for r squared. So if I square this side, I have to square this side. And therefore I end up with just h squared plus r squared. Okay? All right, okay, so I have this expression, and now I have to integrate because I want to get the electric field at that point from all the little points. All right, so here we go. There's a lot of constants here, so we're going to do Ey is going to be equal to K lambda R H over H squared plus R squared, 3 over 2 integral of d theta. And I want to go all around the circle, so what are the limits of my integral? 0 to 2 pi. Okay? And so what I end up with is the electric field at that point is equal to K lambda R H over H squared plus R squared to the 3 halves multiplied by 2 pi. Right? I skipped a few steps between here and here. Basically, what's the integral of d theta? Theta, all right? And then I replace it by this minus it by this, but if you replace it with 0, it's just 0, so it's basically just, I just added that in the place of that integral. Okay? Great, we solved how to find the electric field at one point on a ring, which is literally the easiest shape that we can come up with. All right? Yeah, all that math. Great. Can you guys do this now? Let's try a different example. That was a ring, and a ring is easy. Let's do a disc. Oh. Let's do a disc where there's not a ring. It's a full disc, all right? And I want to find the electric field at point P. Oops, not E. At point P. And I want to find the electric field there. That is another beast, all right? So let's start off the same way as we did. dE is equal to K dQ over R squared. All right, and remember, this is H, radius is R. So if we start off the same way, life is good. Little did you know, when it's dE, and you want to find dQ, and it's an area, what was the area of a circle again? R squared, or it's also the circumference of the circle multiplied by the thickness, right? So it could also be that it's sigma, right? Because it's the charge density of a surface, times the circumference, so which is 2 pi r, times dr, so the thickness, right? Because we're trying to find, if we take one ring that makes up, so if you put a lot of concentric rings, And then a lot of concentric rings, they're going to give you a disk, right? So if I took a random ring here and I found the area of it, which is the circumference multiplied by its thickness, so the circumference multiplied by its thickness, yeah, it's sigma. Yeah. So my sigmas are not very nice. Sigma is supposed to look like this. All right. Yeah, that's sigma. Okay. So I've taken this small ring, all right, and now I'm dividing it by the radius of that small ring, right? The radius of that small ring, what do you want to call that? Small ring radius. I'm getting confused with my R's now. So this here is not the same R as this R. And I just want to change my R's a little bit. I'm going to make this capital R. The radius of the circle, I'm going to make that capital R. The full disk, that's going to have a radius of capital R, all right? And the radius of this small disk, we're going to call that little r, okay? So again, it's the charge density multiplied by the area of this little disk. So the area of the little disk is the circumference of that little disk multiplied by its little thickness, circumference of the little disk multiplied by its little thickness, all right? And if that has a radius little r, so the distance between them is going to be r squared plus h squared. Yeah. Yeah, exactly. Non, ça va être la distance. On va appeler ça x, si tu veux. C'est pas la même. And similar to the other problem, where the angles, they all cancel each other out, and you're only left with the y version, you have to do this multiplied by cos theta. Okay? Big R is the radius of the disk itself, the full disk. Yeah. Yep. Yeah, because that's the distance from that point on that one disk. Yeah. However, it's going to get even more complicated. Sorry. This distance, if I were to take this small, if I were to take this small disk here, or this small ring, I have to treat it like I did in the last problem. And in the last problem, a small ring had this other whole thing with the arc lengths and all that. So what you end up with, and I'm going to skip many steps because I'm trying to make a point here, okay? So you're going to end up with dE is equal to k sigma 2 pi, and instead of r, it's going to be d theta dr times cosine theta, which is h over r squared plus h squared. All of this divided by r squared plus h squared. All right. And now you have something that really truly sucks. D theta dr. So, okay, perfect. If we want to find E, then we have to do the double integral of k sigma 2 pi d theta dr over r squared plus h squared to the power of 3 over 2. Because, think about it this way, I have two variables, and that makes sense because not only does it matter which point along this disk I need to figure out, that's your d theta, is which point along this ring, right? And your dr is which concentric ring to give you the full disk, right? So did you guys learn double integral? Nope, you did not, all right? And just to complete it, you need to integrate from 0 to 2 pi and from 0 to r. Okay, so for d theta, you're integrating it around the circle. And for the disk itself, for dr, you need to integrate it from 0 to the outer radius of this disk. Yeah, Zach. Forget it. Okay. Yes. Ça, no. La dernière, oui. Okay. The point I'm trying to make is Gauss's law makes it so that you don't have to do this. All right. And this is a two-dimensional object. If you have a three-dimensional object, then you have to triple integral things. And you guys don't have Cal 3 as an option here, right? No. Okay. So, yeah. Oh, you're right. There is an H. I forgot it. And it doesn't, again, it doesn't matter how I got here because it doesn't, you guys don't know how to solve it, and I don't expect you to know how to solve it. There is an entire other course on this, and it's called Cal 3. Those of you who are going into Pure and Applied, that's going to be your first year university course. You have to take that course. It's a 100 level math class, which means that it's basically like a weird elective kind of thing. It's an easy course by university standards, but it's a really hard course in reality. In any case, it's hard. So let's use Gauss's law to prevent that from happening. All right, so here's Gauss's law. I've written it at the bottom. It's got some strange symbols, and it doesn't really matter what those symbols mean. I'll explain them to you. This is the Greek letter phi, or it's capital Phi rather, and it stands for flux. Yeah? We will be talking about flux capacitor. That's an actual thing. It's not going to let you time travel. And this here is an integral sign, but it's a surface integral sign. Okay, that's what that means. I'll explain to you what that means later. Surface integral. And this here, what symbol is that? What is that? Nope, it's not multiplication. It's bigger than a multiplication sign if you're to know your circle sizes, which you clearly don't. I'm kidding. That is a dot product. Okay? I told you this course is going to get harder. But it's okay. We're dealing with the hardest stuff right now. Okay, so after this, theoretically, it should be easier. Okay, so now what do all these mean? Okay, so electric flux, let's start with that. Here's your buddy Gauss, all right? I will ask you what he looks like on a test. And we need to talk about this thing called flux. Okay. Flux, represented by this Greek letter phi, is the amount of electric field that passes through a certain area. Okay? So think about it as water flowing. Right? So if you have a big pipe, you're going to have more flow through this pipe, right? If you have a thin pipe, you have less flow through this pipe. So area is quite important. If I were to take this sheet now, and I want you to imagine that this sheet is a window. All right, it's not, there's nothing in between, it's a window. All right, and I'm asking you, if I were to put this in front of flowing water and allow water to flow through, right, the amount of flow per area, right, or times the area rather, is going to give you a large flux because it's got a pretty large window, okay? So this is like, if the water is flowing this way, the water is flowing this way, perpendicular to the surface of this water, it's going to have a large flow. Now, if I were to turn it on its side like this, all right? So everyone pays attention, all right? And the water is flowing this way, all right? And this is a window. How much water is going this way through the window if my water is going this way? How much? None, exactly. So the flux in this case becomes zero. Okay? Flux is at its maximum like when it's like this. Flux is at its minimum when it's like this. All right? And if we were on an angle, is it between those two? If it was like this? Yeah, okay. But did I change the area of this area? No, I didn't. And this is where the dot product thing comes in. Okay, so the area of this didn't matter. It's the angle at which I tilted that matters. Okay? So now you have to expand your minds a little bit. Okay? When I talk about forces, there's a direction, correct? When I talk about electric field, there's a correction, correct? So electric field flows in the direction. When I talk about area, is there a direction? Now there is. Okay, I'm saying that there is. All right. And this is how I'm asking you to expand your mind a little bit. Imagine that this area has a magnitude, and the magnitude is the actual area. So let's say 20 centimeters by 30 centimeters. So in this case, that would be what, 600 centimeters squared, right? So this is 600 centimeters squared approximately. And whether it's like this or this or this or whatever direction it's in, it's always going to be 600 centimeters squared. The direction of it is defined by a normal that comes straight out of the surface like this. Okay? So a surface's direction is defined by a normal line coming out of it. So if I were to say this is 600 centimeters squared, what is its direction? Upward. To the side or whatever, right? But the point is that the magnitude didn't change, but the direction changed. Okay? So that's how area can have a vector. Now, if this is the vector for the flux, for the area, and the flow of the water is coming in this way, what is the angle created by the electric field and the area? Zero. Okay? So we have to find a way to make it so that when we multiply it by some value angle 0, then it should be the maximum of that quantity, because this is going to be the maximum flux that you can get at this angle using this window. And if we're at this angle, what's the flux of this angle? And what's the angle between the electric field and the area? 90 degrees. Okay? So that means I need to employ some kind of mathematical trick whereby I could take this flux, which is expressed as phi, right? And that will equal to E multiplied, or the magnitude of A multiplied by the magnitude of A multiplied by cosine of theta. Okay? And you guys said that when that angle is 0, the flux is at its maximum. So what is the cosine of 0? 1. Exactly. The cosine of 0 is 1. Now what is the cosine of 90? 0. That makes sense, right? So when the surface that is at 90 degrees with the electric field, right? And the flow is coming this way, the angle is 90 degrees to the flow, and therefore the flux is 0. Okay? So whatever the electric field might be, whatever the area might be, it doesn't matter, because if the angle is 90 degrees, the flux is 0. Yeah. It's a dot product. And dot product is exactly what I just mentioned to you. It's this manipulation of the angles. Okay? You'll learn that more in linear algebra. You want to say, oh yeah, it has to do with the angle between two vectors. All right, so you're gonna when Mr. Zentner is gonna present to you guys today, we're gonna do dot product. You're gonna be like, I know what that is. That's the multiplication of two vectors depending on the angle between them. Okay. If the angle is 90 degrees, sorry, if the angle is 0 degrees, right? So it just becomes, so if theta is equal to 90 degrees, or not 90 degrees, sorry, 0 degrees. If theta is equal to 0 degrees, then flux is just equal to E times A. And that's an actual regular multiplication sign, not a dot product. Okay? Following so far? stop me if I've lost you and then ask the question. What is the meaning of life? Why am I here? I'm going to skip over this practice, the question part of this, and ask you just a conceptual question about it. Okay? Yes. Yeah. It's defined by where is that, the face of that area pointing to. Okay? So if, like I said, we define the direction of that area based on a normal vector line coming perpendicular out of the surface. This is when I turn the surface, this normal vector changes direction. So the direction of the surface is defined by the direction of this. Okay, so coming up to this picture here, I can't zoom in and write, so I'm just going to have to keep it this way. But think about it this way. There is this line. This is a line, not a cylinder, this one here. It's drawn as a cylinder, but it's because it's zoomed in. Think of it as a very thin, long wire. All right, and it has this charge, and it's positive, and it's got a charge density lambda, like we're used to, and all that stuff. So if you had this wire made up of many charges, and you were to look at the wire through the cross section, okay? So if I were to look at the cross section of the wire, if I just cut the wire like this and looked into it, right, and it's just a very thin, positively charged wire, right, then the electric field is going to be radially outwards. Right. Radially outwards. We learned this. So far, so good, right? And I have this thing here, this cylinder here, and assume that this is kind of like, nope, don't assume it. This cylinder on the outside is a toilet paper roll, all right? You finish your toilet paper, you have this cylinder left over, it's empty on both sides, it's infinitely thin, right? And I'm gonna put this toilet paper roll around this wire. So all the surfaces of this wire and all the surfaces of this toilet paper roll are exactly parallel. You guys agree with me? Yes? No? Okay, so this toilet paper roll, the surface of this toilet paper roll, and the surface of this wire is all totally parallel. If I were to take a small bit of this toilet paper roll, and I wanted to measure the area of that, and we're going to call that area dA. Okay, what would for that point, for that dA, what would be the direction of its area? Would it be tangent to the surface of the toilet paper roll? Would it be pointing out from the toilet paper roll, in from the toilet paper roll? So remember that if I had a surface, the direction of the area is perpendicular to the surface. So if I took a chunk of this, what direction would it be? Okay? Outwards, away from the toilet paper, right? So I'm going to change my pen color because I'm not writing exactly. So the area vector is going to be perpendicular outwards from the toilet paper roll. Okay? And if there is an electric field coming in radially outward, what can you say the relationship is between the electric field coming out of the wire and the area of this toilet paper roll? What is it? Perpendicular, parallel, at some angle? What do you think? You're saying 90 degrees? You're saying 90 degrees? Look at my arrows. Are they at 90 degrees? No. It's perpendicular to the surface, but that means that it's parallel to the surface vector, right? To the surface vector, right? So here we go. Here's the surface of the toilet paper, all right? I can curve it if you want to make it more realistic, all right? at any point, so if I were to draw the surface vector all around it, it would look like this, right? That's the surface vector, right? You guys following me? All right. And because there's a wire that's going through that's shooting electric fields outwards, then the electric field is also the same. So at any point along this surface, this toilet paper roll, the electric field is parallel to the surface vector, to the area vector. Okay, perfect. So that means all along this surface, or if I were to write, the surface integral of EdA, okay, and that's where that symbol comes in, the surface integral of EdA, it's always going to be parallel. No matter where you look on this toilet paper roll, it's always going to be parallel. All right, so the integral of everything along that surface is just going to be equal to E times A. All right, and A would be the area of this toilet paper roll. Yes, I wrote toilet paper roll. This toilet paper roll, we chose it to conveniently do that. Okay, I chose it to be that shape because I wanted that at every single point that it's going to be parallel to the electric field line. This is what you call a Gaussian surface. Okay, and a Gaussian surface is a surface that you choose. Okay, you choose your Gaussian surface because it's convenient for the math. If I were to integrate all of those little dAs, then it's a convenient shape. It's a cylinder. All right, let's move on. If I took a point charge, there it is in the middle, a point charge, right? What surface could I choose? So there's my point charge. What kind of shape could I choose so that the electric field lines coming out of this point charge is always going to be parallel to the area vector? A circle, think 3D? A sphere, exactly. So if I have a charge in the middle, I put a Gaussian sphere around it, all right? Then at any point, this electric field here and the surface, let's say the surface, I'm testing the surface at this point here. The surface at that point there, well, the area vector is in that direction, so they're parallel. So again, the surface integral of E times dA is going to just be E times A. Because at any point, I want, it's going to be parallel. Again, remember, we're doing the hard part together. The application of this is going to be very, very straightforward. Yeah, exactly. A tiny area on the floor. Cedric? Yeah, so once you integrate it over the surface, then it's the whole area of the sphere. Area, not volume. So what's the area of the sphere again? 4 pi r squared. Okay? Another thing I want you guys to know, I'm going to get back to this actually afterwards. Okay, so here's exactly what I wrote. This is the drawing the electric field coming out of that charge, right, into that small dA is going to be parallel. So I can say that the surface integral of E dA is just equal to E times A. And this is equal to the flux. And E, or no, not E, but EA, is equal to should I do it that way? I don't want to confuse this. I don't want to do that. Okay, let's do it. No, I'm actually gonna do this later because I don't want to do it now. Let's stop it there for this proof here. Okay, so we have this that EA is equal to the flux when the Gaussian surface is always parallel to the charge. If I had a line, right, my Gaussian surface that I would choose is a cylinder. And again, in this case, the surface integral of EdA is equal to E times A. Again, we still haven't come up with what Gauss's law really is yet. So now, I'm just going to give you 1 second to write this. Yep. Oh, this. Oh, that's like if I put a point charge in the middle of a sphere, right? Then all the electric fields coming out of that point charge are going to penetrate this little area point of my sphere at a parallel angle. That's all that means. Okay. So again, this is a wire with a toilet paper around it. And now we're going to get to the actual Gauss's law, which says that the flux is only a matter of the charge enclosed in this Gaussian surface. So we decided a Gaussian surface. So perfect. The electric field coming out of that, or the flux coming out of that, or the electric field times the area, is only equal to the charge enclosed divided by this constant epsilon naught. All right. So I'm just going to write that here. That's, can you guys see that? No. So this is charge enclosed inside the Gaussian surface. Okay? And the flux only depends on that. That's crazy assumption because that's a very vague generalization. Something as complicated as flux depends only on the charge of what's inside this Gaussian surface. So I'm going to go back a couple slides now. I'm going to go back to this here. What is the charge inside this sphere? Is what? It's positive. Let's call it Q. Okay? So the charge inside this surface, or this sphere, we're going to call it Q. And therefore the flux is that Q divided by an epsilon naught. Okay? If I were to define my surface in a different way, let's call it S3, and this is my surface, how many charge is inside of it? Okay, Q. So the flux coming out of this Gaussian surface versus the flux coming out of this Gaussian surface versus the flux coming out of this Gaussian surface is all the same because it only depends on the charge inside of it. But that has to do with flux. Now we have to deal with the area if we want to talk about electric field, because we said that if we go here, right? We said that that not only is flux equal to this, but this kind of integral that we came up with is equal to this. If you choose your Gaussian surface correctly, so that all of your electric field lines are parallel to the area lines, right? So if you choose it so that all the surface integrals of EDA is equal to EA, right? Then remember, you choose your Gaussian surface because all that matters is the charge inside. Then if you choose it correctly, you can get this relationship. And this is such a convenient relationship, right? The electric field multiplied by the Gaussian surface's area is equal to the charge enclosed over some constant. That's amazing. Look how simple that is. You can find the electric field of anything as long as you put a smart Gaussian surface over it. I'm saying Gaussian surface a lot, and you guys are like, what the is that, right? And that's fine. That's normal. Coming back here. I'm going to draw this differently, okay? Here's your, whoa, come on you a little bit. Here's your positive charge. I'm just redrawing this. I'm redrawing this over here. Are we almost done? No, we're good. We're perfect on time. I'm redrawing this here, and there's a positive charge, all right? And I'm asking you, what is the electric field at a point P at a distance R? Okay, so here I'm asking you, what is the electric field here at a point P at a distance R from it? And we can use KQ over R squared to find the electric field. That's fine, but you know, there's other ways of doing it. So let's just say we know that TA is equal to Q enclosed over epsilon naught. We know that. That's Gauss's law, and we're going to use that. And E is what we're solving for, multiplied by the area. So now what I want you guys to do is take this point here and make that into a Gaussian surface. So at this point, if you were to take any measurement on a sphere all around this point, if I were to take a sphere and has a radius r so that the P is on that sphere, right? I can say that E times 4 pi r squared is equal to Q inside over epsilon naught, right? Because the area of my Gaussian surface is just the area, the surface area of that sphere that I chose for this Gaussian surface. And the radius is that distance at which my point is on that surface. Well, this is really cool because let's rearrange it a little bit. Let's take that, because we're solving for electric field, let's shove that down there. So now you have Q enclosed over 4 pi epsilon naught r squared. I don't know if maybe one of you, hopefully at least one of you remembers this. There was this epsilon naught constant that we had like 5 classes ago. I told you that 1 over 4 pi epsilon naught is equal to k. Well, there it is, 1 over 4 pi epsilon naught. So this is in fact how you get kq over r squared, not kq squared, but kq over r squared. That's how you get it. Sorry. Are your minds blown? I think this is cool. So this allows you to determine any electric field from a charge at a radial distance r. Okay? But in order for this to hold true, what does the shape of the charge need to be absolutely? The shape of the charge. The Gaussian surface has to be a sphere, And we chose the sphere because the charge is what shape? A point charge. So this actually only applies for point charges. Yeah. So far, so good? The relationship you want to remember is this. This is Gauss's law right here. Big arrows towards this. You need to know how to use that. Okay, moving forward. I'm asking you here, what is the flux of this? Remember that flux, you guys see that? Okay. Flux is equal to Q inside over epsilon naught. And what's the Q inside of this random weird spherical shape? Random weird shape. Not spherical, but random weird shape. What's the charge inside? It's -8 plus 2, which means that it's -6. So it's -6 coulombs over epsilon naught is equal to the charge, yeah, equal to the flux coming out of that surface. Yeah. This Gaussian surface can be any shape. All right. I won't be able to do that fancy surface integral and remove the surface integral dot product thing unless it's a nice shape that I can add up to. But I'm not looking at shape here. I'm looking at flux. That's the Gaussian surface, exactly. This shape that I created around is that Gaussian surface. Okay. If I were to say your 2-point charges equal in magnitude, what is the flux coming out of this Gaussian surface? You would say what? Charge over epsilon naught. All right, so for this one, it's going to be positive charge over epsilon naught. What about for this Gaussian surface here? Yeah, that's going to be negative charge over epsilon naught. That's going to be the flux coming out of there. What about this Gaussian surface here? No flux, right? But are there electric field lines penetrating the surface of the Gaussian surface? But look at that, they're going outwards, so they cancel each other out. Okay, so the flux coming in and the flux going out, the same. So the net flux is 0. All right. What about this? Zero again. So the S4, the flux on S4 is equal to 0 because the charge inside is 0. 0 over epsilon naught is 0. The two charges, they cancel each other out. So far, so good? Try to do these. Which one of these has the highest flux coming out of the Gaussian surface? I'm trying to trick you. Don't let me trick you. B? Cedric says B. His answer is correct. Is it 100% correct? Yeah? How would you compare B with E. What's the formula for flux? Q inside over epsilon naught. Does it talk about radius? No. Q inside, that's all that matters. So B and E are equally the highest, and everything else is the same and lower. So if I wanted to write it, it would be B is equal to E, and those are greater than A, which is equal to C, which is equal to D. Yep. Yep. You choose your Gaussian surface, and inside that Gaussian surface, it's just positive Q. Yep. It's a constant. I believe it's 8.85 times 10 to the negative 10. Let's go with 10. Can you just look that up real quick? It's called permittivity of free space. 8.85 times, okay, negative 12, not 10.
And like, do we have to know it?
Yeah, we're going to be using all that. So Kevin asked a good question. What is the value of this epsilon naught? Epsilon naught is 8.85 times 10 to the negative 12 with a bunch of units. It's easy to come up with epsilon naught because it's just k divided by, k times 4 pi, and 1 divided by that number. You can remember it as epsilon naught is equal to 1 over 4 pi k. So the flux in a cube will be the same as a flux in a sphere, because all that matters is the charge inside that surface. So if I chose my Gaussian surface to be a cube, it's silly that I would do that, but okay, fine. The area of a cube, the volume of a cube, the area of a cube is easy to find, right? So we can maybe use this. There's not a lot of symmetry though, because not every point is equidistant from the center of where you would put the charge. But you can still use it, and the flux will still be the same as if that surface is a sphere. However, if I were to ask you, and I'll be tricky, and I'll say, what is the flux through one of the sides of the cube, then you'd have to take the flux of the whole cube and divide it by 6. Okay? If I were to ask you, is this red or well, I just want to ask you guys a question. If I had a cube, if I had a cube, does it matter where inside that cube I place the charge to determine the flux? Like if the charge was like right there in the corner versus right in the center, does that make a difference? No, again, Q enclosed. That's it. There is no radius, there's no distance, there's nothing. Right? What if I place my Gaussian surface outside of the, yeah, you know what I mean? Si je demande, oh crap, what happened to it? It's coming back now. See, if I ask you, what's the flux coming out of this cube? Because the lines are going to go outwards, right? So this thing has an electric field, and it's going to go in all different directions. Oh, this is bugging hard right now. The electric field lines are coming in all directions going outwards, right? So the flux coming out of it is the same as if I were to draw a sphere around. But if I were to ask you how much flux is coming out of only one of the 6 faces, then you would say 1/6 of that amount. Okay? Yeah, Cedric. You choose a Gaussian surface. So if I told you find me the electric field at a certain point R, if you choose a Gaussian cube, you're not doing this smartly. Should be using a sphere. Okay? So here we have another Gaussian surface. The Gaussian surface is on the outside of the charge. First of all, what's the charge inside my Gaussian surface? 0. So therefore the flux is 0. And the way to know that is that you have electric field lines coming in. Doesn't matter though, because this is a closed surface, it's going to come out at some point. And so the net flux is 0. Okay? I think I'll stop there. Brew with that for a little bit. And try to digest that well and come back next class ready to apply this. Yeah, I was just wondering for the last part. Give me 1 second, actually.